So are there any questions? Well, okay, as I can't hear any questions and I can't see any questions in the chat, we can continue. Just for those who might have not caught it at the first lecture, we have consulting hours. I send you an invitation through my MS Teams for each Monday evening, 5:45. And if no one shows, like yesterday, I finish at 6 o'clock with the mood waiting. So anyway, that's not compulsory, just that's a chance to have consultation with me. And now I'm switching back to electromagnetic field. As there are no questions, I will change and add new paper because we have just went to the end of the pile and continue that. So we've got a new paper. We have been investigating electrostatic fields some time ago, and after solving the simplest points, we have arrived to a point where two different media have had a common interface and investigated boundary conditions. Now, the same kind of conditions should be investigated now, and what we are going to do now is to derive boundary conditions at an interface between two conductors with different specific conductivity. So, like before, we have an interface, a layer or a plane dividing the universe into two parts, up and down, or number 1 and number 2. And within those two parts of the universe, we have most of the quantities marked 1 or 2. So we have electric field strength upstairs as E1 and electric field strength downstairs marked as E2. Now again, we would have to divide those vector components, which here in steady current field would be electric field strength E and current density J, into two parts, tangential and normal. So for example, this would be E1 normal, and this would be E1 tangential. This is E2 normal and E2 tangential. Now just note that upstairs the chosen direction of the electric field strength goes from infinity to the boundary, and downstairs the flux points from the boundary to minus infinity. Well, so we have those two values. We of course have one scalar value that is common to those two places, and that's the potential. As we have noted within electrostatics, there is no possible abrupt change in potential, because that would mean an infinite electric field strength and therefore an infinite energy density. Well, that would in reality mean an electric discharge. So we have a potential which has no index because potential is continuous over the surface. So we will not touch it anymore, and we will first ask what the behavior of electric strength tangential components would be. Well, and after all, it's the same story like in electrostatics. If there is a potential value, for example here, which must be the same over the interface and under the interface, because the potential is continuous, and as the electric field strength is minus derivative of the potential, in fact the electric field strength tells us how fast the change of potential is, and you cannot have different speeds of change of potential upstairs and downstairs unless you finish with different values of potential at any other point. So not only the potential, but all the derivatives, first, second, third, must be identical at the interface. Well, we do not care about the 27th derivative at the moment. The first derivative, which is minus electric field strength, is important, and they must be identical. So tangential components of electric field strength at the interface between two conductors must be identical. So we have first boundary condition that tells us that E1 tangential is E2 tangential. Now, having the Ohm's law, E times conductivity is current density, we can specify the boundary condition for current densities, at least for the tangential part of current densities at the interface. They must be proportional to conductivities, to specific conductivities in the upper and lower part. So the condition is now J1 tangential over J2 tangential is sigma 1 over sigma 2. So the more conductive the media is, the bigger current density at the interface in this media would be. So we have now established conditions for tangential field components at the interface. Still, we have to add a condition or a set of two conditions for normal field components. Now, within static current field, we have a simple condition. Let's say that we have a small volume for example, a cube that at the interface, in fact, is half buried under, half stretching over the interface, and its bottom and cap are parallel to the interface. Then the walls would be perpendicular to the interface. And as to normal field components, the current would flow parallel to those four walls, would not intersect it, so the current would not flow into or out of the brick, the cube, at the side walls. But it will flow in at the cap and it will flow out at the bottom. Because we handle steady current, we have to find out that all the current that flows in through the cap must flow out through the bottom. Otherwise, there would be an accumulation of charge inside the cube. And as we have steady current, it is something that lasts infinitely long, the charge would have infinite value, which would result in a discharge. So that's impossible. So we know that the current density flowing from upstairs down into the cube must flow down through the bottom side of the cube unchanged. And therefore, it must hold that J1 normal is strictly equivalent to J2 normal at the interface. Having strictly equivalent normal components of current density, we can now establish the condition for electric field strength. Again, we would use the Ohm's law in differential form, and we get E1 normal over E2 normal as a ratio of sigma 2 over sigma 1. So, as a quick fix, a rule of thumb, if there is an interface between two conductors of different conductivity, the electric field strength would be bigger at the side of lower conductivity. So now we have established one condition for potential that is constant over the interface. We have another condition that binds tangential field components, that is electric field strength and current density. And we have another set of conditions that binds normal components, that is, again, current density and electric field strength. The set of boundary conditions at the moment is complete. Are there any questions?
Yeah, yes, please. You said that the electric field will be bigger at the lower part, so
No,
it means that
no, not exactly. I did not tell it will be bigger at the lower part. It will be bigger within the material with lower conductivity.
Okay.
And that referred to normal components because as to tangential components, those two fields are identical at the interface.
Okay, thank you very much.
Yeah, welcome. Are there any more questions?
No, not for a moment.
Seems not at the moment. Okay, so that we will be able to continue with the topic a little bit more. Now, I will turn the paper over and attract your attention to an important point. Both fields, electric current, static electric current field, and electrostatic field, are governed by the same kind of equation. And that is the Laplace equation. This is the equation that forms or describes both current and electrostatic field. Now, That means that we can use those fields to substitute each other. This is not used much today, but I remember, for example, we have a neighbor, in fact, a daughter of Czech Technical University, which is the School of Chemical Engineering, just over our street. And one of their important institutes is interested in glass. And at the beginning of glass production, you have a glass furnace that melts glass, and then it could be processed further. Now, if you try to melt glass, you need to achieve quite a big temperature. And modern glasses are quite sensitive to any contamination. So it's difficult to heat that by coal, it's even difficult to heat that by gas. What remains as a good source of heating is electric current. So we arrive to electric glass furnaces. And that is carried out in the way that you have melted glass, you insert inside electrodes. Well, you have to make them out of wolfram because it withstands melted glass. And then you put voltage and feed current into those electrodes. As that's not something small on your table, it's something like a building. You have quite thick electrodes, a lot of transformers, a three-phase sources feeding the current into those electrodes. And as that's something very expensive and you need to get more or less homogeneous temperature in the furnace, it needs some calculation or some analysis before you build it. And one of the ways to handle that was making models so that the scientist would have a kind of aquarium on his table with small electrodes and feeding that by small transformers, and that solved both the electrostatic and current field within the furnace. So in fact we have been used to model that because modeling was much faster than calculating. When I was of the age of you, the field in a furnace could be solved using numerical methods. Just one solution took about 3 weeks, which was not that practical. One model establishment took 1 or 2 days, and then you could only move electrodes easily, and you had the result instantly. We even have been using, for 2D problems, we have been using paper that was conductive, and we glued aluminium electrodes on it and just measured by a voltmeter the distribution, which is now a museum type of exponent because there are numerical methods for solving of the Laplace equation. And I only told you about the mechanical or old modeling methods to draw attention to the fact that there are numerical methods that can do that quite easily, provided you have a fast computer with enough memory. And that's something which is now your mobile phone, for example. So this is something that can be done easily. Now I would like to deliver a short introduction to the, let's say, simplest method of field solution. As my abilities to draw a 3D pictures are quite limited, I would carry out the description of the method only in 2D, but it can be extended quite easily to 3D. So let's say that we want to find out a solution of a Laplace equation in some region. Now, there is an old mathematical joke that says, well, there are two kinds of differential equations. Well, the first of them can be solved analytically, and that's what we teach at schools. And then there are the equations that arise from practice. Well, and most of them could not be solved analytically. We can find an analytic solution to this equation for 1D easily. We can find an analytic solution for 2D problems, provided that the shape is more or less composed of rectangular pieces. But for a curvilinear shapes, this is not possible. So we have a problem. We need a solution. We need it very much. I mean, it affects billions of crowns or dollars within furnaces. But we can't find it analytically. But possibly we would be happy enough if we have not the exact analytic solution, but if we had only a solution that is prepared with some accuracy we can trust. So, how to do that? The first method is called the method of finite differences, or a method of nets. Well, how that works? So let's say we have an area within which we need to calculate the electromagnetic field. And as you can see, it's not very regularly shaped. Now, in order to find the field, we would have to give up establishing a function that would describe everything. But what we can do is just to cut the area by a set of cuts. Let's start with cuts that are equidistant. And now let us consider only the values of the potential in the intersections of the cuts. Let's say the grid points. If we cut the area with more cuts, we would get more grid points, and therefore we would have more close points where we would know the field with some precision. So this is not an exact solution, but it could work quite well. And now this is the first point. So we replace a continuous solution. We give up finding an exact function that describes the potential, but we hope to find good potential values in a number of points within the area under investigation. Well, now let us focus on a set of 5 points So this is a set of 5 points, one in the center, and it has got 4 neighbors in its neighborhood, the closest points to this central point. Now, what would you think about the values of potential in those 4 points? What would be the value in the center point as with respect to the other points? And possibly you would tend to have some empirical idea, which is it should be the average. Possibly the potential in this point should be the average of its neighbors, especially in the case when we make a very fine cut so that those points are quite close each to the other. So the first idea we have is, let's think this is the average. Now, this is an empirical idea, an empirical of first ideas in many cases are correct and sometimes are not as correct. So what I will do now, I will support this idea by a result of mathematical calculation, and I will derive it using series, a Taylor series, which then would give rise to not only the equation for calculation of the central point potential value, but also will yield an estimate of the error we made it. So, okay, let's start with the Taylor series. So, let's write a Taylor series for the field around the central point. To be able to do that and make calculations and make equations, we have to name the point somehow. So let's name the central point 0, so there will be phi 0, the value of potential in it, and let's mark the others. So this will be 1, 2, 3, and 4. We have also to introduce coordinate system. So let's have x over here and y over here. And let's have it introduced in the manner that the x and y in the central point are set to 0. So we have the coordinate system beginning here. This is x, this is y. Now we will have to find out the value of some derivatives. First, let's say that we will write the Taylor series for the value of the potential in the point 2, so that is phi 2, as a Taylor series. How do we do it? Just remember, the series looked like the function in some point is the function value in the beginning plus first derivative times the distance between the points, which is the second estimate. Now we have another estimate, more accurate. We add plus second derivative of the function divided by the distance squared and 2 factorial. Then we have the third derivative, the fifth, and so on. So let's start to put down the series. We have phi 2, and it should be the value at the starting point. So the starting value is phi 0 plus, well, we have to somehow call the distance, the step between those two cuts, and I will call it h. So we have the same step in all 4 directions, h. So there will be h times the first derivative of phi. Now I would denote df over dx by an apostrophe. So we would have the first derivative of phi. Well, but more precisely, there should be also plus h over 2 factorial. 2 factorial is 2 times 1, which is 2. Phi, second derivative of phi, which by the definition is phi with 2 apostrophes. And that's not enough. To be more precise, we continue. So we will have also plus h raised to the third order divided by 3 factorial, which is 6, phi 3 times derived against x, and I would instantly add h raised to the fourth power divided by 24, which is 4 factorial, phi 4 times derived, and we will mention that the series continues, but my paper does not continue anymore, so this is the first series depicting the field value in point 2 as a Taylor series around point 0. Now, let's do the same for point 1. So we use the same kind of series. The only difference, in fact, is that now we move against the x, so that the distance is negative. When we have second or fourth power of the distance, we get the same like before. When we have first or third, we get minus there. So now I would directly put down the equation for the potential in point phi 1 with no comments. So this is a set of two equations for points 1 and 2. Now we would have to handle points 3 and 4, and those points have the same x coordinate like point 0, but they differ in the y coordinate. So we would have to establish some way how to denote derivatives to save space. So a derivative of a function f against y would be denoted like phi with a dot, not apostrophe but a dot. So using dots to denote derivatives, I would again put down two equations. The 0.54 has a positive deviation in y-axis, so there would be the same notation like phi 2, just we would substitute apostrophes with dots. I'm going to put that down again in red, and I will read it loudly so that you can keep track even if you don't read that with your resolution. So we will have 0.54, and again that's phi 0 plus h times the first derivative of phi against y plus h squared over 2, the second derivative of phi against y, plus h raised to the third power divided by 6, phi 3 times derived against y, plus h raised to the fourth power divided by 24, phi 4 times derived against y, and there is the rest of the series. And now I will put down an analogic equation for phi 3. We know that the equation would only differ in those two signs, where there will be minus instead of plus. So I put it down now without comments. Well, and we are close to our end position. We have 4 equations. Now, what we can do easily is add all of them together. So, first, we will add the items on the left side, and we will get a sum of phi 1 to phi 4. So let's do it. So the left side now becomes phi 1 plus phi 2